Imagine the most powerful thing in the universe, not an explosion, not a star, not even a galaxy. Imagine something so heavy, so dense that even light itself cannot escape its pull. Something invisible, yet capable of shaping the motion of stars, bending time, and controlling entire galaxies. This is a black hole. And unlike science fiction, black holes are not imaginary monsters hiding in deep space. They are real. They exist right now, and their influence is everywhere. At the center of almost every large galaxy, including our own Milky Way, there is a gigantic black hole, millions or even billions of times heavier than our Sun. At the same time, scattered across the universe, there are much smaller black holes formed when massive stars die violent deaths. Both are called black holes. Both follow the same laws of physics, but they are not the same thing. So here is a simple question, one that sounds easy but opens the door to a deep cosmic mystery. Is the black hole at the center of a galaxy the same kind of object as the black hole formed from a dead star? At first glance, you might think yes. A black hole is a black hole, right? Gravity is gravity. But when scientists looked closer, they realized something strange. These two types of black holes are different in size, different in origin, different in age, and different in how they shape the universe around them. One is born from destruction. The other seems to have existed almost since the universe itself began. This video is not about fear. Black holes are often shown as cosmic killers that swallow everything in their path. In reality, most black holes are quiet. They do not chase stars. They do not hunt planets. They sit in space following the same rules as everything else, yet operating at extreme limits of gravity and time. Understanding them is not about being scared. It is about understanding scale, origin, and power. Today we are going to compare two giants of the universe, stellar black holes and supermassive black holes. We will explore how they are born, how big they really are, where they live, and how they affect the universe in very different ways. We will do this without complex equations, without technical jargon, and without confusion. Just clear ideas, simple examples, and visuals that make sense. By the end of this video, you will clearly understand why a black hole formed from a dying star is not the same as the monster sitting at the heart of a galaxy. You will see how the same laws of physics can create objects that feel completely different in scale and influence. And most importantly, you will walk away with a deeper appreciation for how strange, elegant, and powerful our universe truly is. So let's begin not with fear, but with curiosity. Because when we understand black holes, we are really learning how the universe builds its most extreme creations. When people hear the words black hole, their imagination usually jumps straight to danger. They picture a giant dark hole in space that pulls everything towards it, swallowing stars, planets, and even entire galaxies without mercy. This image is powerful, dramatic, and memorable, but it is also deeply misleading. To understand black holes properly, the first thing we must do is unlearn what movies and fiction have taught us. A black hole is not a hole. It is not a tunnel. It is not a doorway to another universe waiting to suck everything inside. A black hole is an object, one of the most extreme objects nature can create, but still an object that follows the same fundamental laws as everything else in the universe. At its most basic level, a black hole is matter compressed to an extreme degree. Gravity is the key idea here. Everything with mass has gravity. A small rock has gravity, but it is so weak that we never notice it. Earth has much more mass, so its gravity is strong enough to hold us on the surface and keep the moon in orbit. The sun has even more mass, giving it enough gravity to hold the entire solar system together. A black hole is what happens when gravity wins completely, when matter is squeezed so tightly that gravity becomes overwhelming. To understand this, imagine compressing Earth into the size of a marble. It would still have the same mass, but now that mass would be packed into a much smaller space. Gravity at the surface would become incredibly strong. If you kept compressing Earth smaller and smaller, at some point the gravity would become so powerful that nothing could escape from its surface, not even light. That is the basic idea behind a black hole. It is not about emptiness, it is about density. Light plays a crucial role in why black holes appear mysterious. Light is the fastest thing in the universe. Nothing travels faster. When something cannot escape an object's gravity, we lose the ability to see it. A black hole does not shine because light cannot leave it once it gets too close. This is why black holes are invisible by nature. We do not see the black hole itself. We see its effects on the space around it. The boundary where escape becomes impossible is called the event horizon. Despite its dramatic name, the event horizon is not a physical surface. There is no wall, no shell, and no solid boundary floating in space. It is simply a distance from the center of the black hole where gravity becomes too strong for light to escape. The word event is important here. It means that once something crosses this boundary, no event inside can ever affect the outside universe again. Information cannot return, signals cannot escape. The story, as far as the outside universe is concerned, ends there. A useful everyday analogy is a waterfall. Imagine a calm river flowing toward a cliff. Far upstream, the water moves slowly, and a swimmer could easily swim back. As the river approaches the edge, the current speeds up. Eventually, there is a point where the water flows faster than any swimmer can swim. Once you cross that point, falling over the waterfall becomes unavoidable. That point is like the event horizon. Nothing special happens at the exact location itself, but once crossed, escape is no longer possible. This idea surprises many people, but crossing the event horizon is not necessarily violent. There is no sudden crushing force exactly at that boundary. For very large black holes, someone falling in might not notice anything unusual at the moment of crossing. The real danger comes later, much deeper inside, where gravity differences become extreme. This detail already hints at something important. The experience near a black hole depends strongly on its size. Another widespread misunderstanding is that black holes constantly pull everything toward them. This is not true. Black holes do not actively suck in matter. They do not chase stars or wander through space hunting planets. Their gravity behaves just like the gravity of any other object with the same mass. If you replace the Sun with a black hole of the same mass, Earth would continue orbiting in almost exactly the same way. There would be no sudden collapse of the solar system. Gravity does not care whether mass is in the form of a star or a black hole. Distance matters far more than the object's internal nature. So why do black holes sometimes swallow stars or gas? The answer is simple. Just like stars, black holes pull in objects that get too close. Most of space is empty. Stars and planets rarely wander close enough to a black hole to fall in. When they do, it is because their path takes them near enough for gravity to take over, not because the black hole actively reaches out. Most black holes are actually quiet and invisible. They do not glow. They do not emit light. They sit in space, often unnoticed, until something passes nearby. When gas or dust approaches a black hole, it does not fall straight in. Instead, it spirals around, forming a swirling disk. As this material rubs against itself and accelerates, it heats up and begins to glow intensely. This glowing material is called an accretion disk, and it can shine brighter than entire stars or even galaxies. Ironically, black holes are often discovered not because they're dark, but because their surroundings become extremely bright. This distinction is important because it shows that black holes are not defined by destruction alone. They interact with their environment in complex ways. They can shape the motion of nearby stars, influence the formation of new stars, and even affect the structure of entire galaxies. But again, none of this happens magically. It all follows from gravity and motion. At the heart of a black hole lies something even stranger, a region called the singularity. This is the point where, according to our current understanding, matter is crushed to infinite density. The laws of physics as we know them stop working there. It is important to be honest about this. Scientists do not fully understand what happens at the singularity. This does not mean black holes are mysterious in every aspect. It simply means our theories are incomplete at extreme limits. The existence of the singularity reminds us that black holes are not just astrophysical objects, but also laboratories for testing the deepest laws of reality. Now comes a crucial idea that sets the stage for everything that follows. Not all black holes are the same. The phrase black hole describes a concept, not a single object. What defines a black hole is mass and compression, but those quantities can vary enormously. Some black holes are only a few times heavier than the Sun. Their event horizons are small, and their influence is limited to a relatively tiny region of space. Others are millions or billions of times heavier, with event horizons larger than our entire solar system. These massive black holes sit at the centers of galaxies and quietly control the motion of billions of stars. Despite these differences, all black holes share the same basic structure. They have mass, they have gravity, they have an event horizon. They follow the same rules of physics. What changes is scale, and scale changes everything. The strength of tidal forces, the behavior of nearby matter, the timescales of growth, and even the experience of falling in all depend on how massive a black hole is. Understanding what a black hole really is allows us to let go of fear and replace it with curiosity. A black hole is not a cosmic destroyer roaming the universe. It is an extreme outcome of gravity doing what it always does, pulling matter together, holding structures in place, shaping motion and time. When gravity reaches its ultimate limit, the result is strange, beautiful, and deeply informative. This foundation is essential, because from this point forward, the story will branch into two very different paths. One path leads to black holes, born from the violent deaths of massive stars. The other leads to colossal black holes that sit at the centers of galaxies, shaping the universe on the largest scales. They share a name, but their stories could not be more different. And to truly understand that difference, we must first understand what a black hole is at its simplest level. Once we understand what a black hole is at its most basic level, the next step is to realize something even more important. The word black hole does not describe a single type of object. It describes a family of objects that share the same fundamental rules but live very different lives. This is where the real story begins, because when scientists talk about black holes, they are usually talking about two giants of the universe with completely different origins, scales, and roles. These are stellar black holes and supermassive black holes. The words themselves already hint at the difference. Stellar comes from the word star. A stellar black hole is directly connected to the life and death of a star. It is born when a massive star reaches the end of its life and collapses under its own gravity. Its story is personal, local, and violent. It begins with a single star and ends with a compact, powerful object left behind after a cosmic explosion. Supermassive, on the other hand, means exactly what it sounds like. These black holes are not just bigger, they are enormously bigger. A supermassive black hole is millions or even billions of times more massive than our Sun. It is not linked to the death of a single star. It sits at the center of a galaxy and seems to be connected to the galaxy's entire history. Its story is slow, ancient, and deeply tied to the structure of the universe itself. At first, this difference can be hard to accept. After all, both objects are called black holes. Both have event horizons. Both trap light. Both bend space and time. So why do scientists treat them as separate categories, instead of just calling one small and the other big? The answer lies in scale, origin, and influence. These differences are so extreme that putting them in the same category, without distinction, would hide what truly makes each one special. Let's start with size. A stellar black hole is surprisingly small. Even though it can have several times the mass of our Sun, all that mass is packed into a region only a few tens of kilometers across. If you placed a typical stellar black hole where Earth is now, you would not see a giant object filling space. You would see nothing at all, because it would be tiny compared to planets and stars. Its event horizon would be smaller than a city. Yet within that small size lies immense gravity. A supermassive black hole, in contrast, completely breaks our intuition. Its event horizon can be larger than the orbit of Mercury, Venus, Earth, or even Neptune, depending on its mass. Some supermassive black holes are so large that our entire solar system could fit inside them many times over. And yet, despite this enormous size, they are still black holes following the same rules as their much smaller cousins. The difference is not just a matter of scale, it is a difference that changes how these objects behave and how they interact with their surroundings. Mass makes this difference even clearer. Stellar black holes typically range from a few times the mass of the Sun to perhaps a few dozen times the Sun's mass. Even the largest stellar black holes known today remain within this range. Supermassive black holes start where stellar black holes end. The smallest supermassive black holes are millions of times more massive than the Sun, and the largest reach billions of solar masses. There is no smooth bridge between these two ranges. They exist in completely different mass worlds. This massive gap is one of the reasons scientists separate them into different categories. If supermassive black holes were simply grown-up stellar black holes, we would expect to see many objects in between, slowly filling the gap. But that is not what we observe. Instead, we see two dominant populations: small star-born black holes scattered throughout galaxies and enormous black holes sitting at galactic centers. This separation strongly suggests that their life stories are fundamentally different. Location adds another layer to the story. Stellar black holes are found throughout galaxies. They orbit the galactic center just like stars do. Some are isolated. Others exist in systems with companion stars, where they pull gas from their neighbors. Their influence is local. They affect nearby objects, but they do not control the structure of the galaxy itself. Supermassive black holes, however, have a very specific address. They live at the center of galaxies. Almost every large galaxy we observe appears to host one. These black holes do not wander. They sit at the gravitational heart of the galaxy, anchoring the motion of billions of stars. The stars orbit the galaxy's center, and at that center is a supermassive black hole. This central position gives them a role far beyond what their size alone might suggest. Because of this, supermassive black holes are not just objects inside galaxies. They are part of what defines a galaxy. The mass of a supermassive black hole is often closely linked to the mass and structure of the galaxy around it. This connection is one of the strongest clues that these black holes and galaxies evolved together over billions of years. Scientists separate stellar and supermassive black holes because their origins appear to be different. Stellar black holes form at the end of a star's life. We understand this process reasonably well. We can observe massive stars, watch supernova explosions, and detect the compact remnants they leave behind. The story, while dramatic, fits neatly into our understanding of stellar evolution. Supermassive black holes are a different story. Their origin remains one of the biggest unsolved problems in modern astronomy. They are already extremely massive very early in the universe's history, long before there was enough time for normal stars to form and die in large numbers. This creates a mystery. How did something so massive form so quickly? Did they grow from smaller seeds? Did they form directly from enormous clouds of gas? Did they begin as something entirely different? These questions are still actively debated. Their daily lives are also very different. A stellar black hole usually lives a quiet existence. It may spend millions or billions of years doing almost nothing noticeable. Occasionally, it may interact with a nearby star, pulling in gas and shining briefly in X-rays. but on cosmic timescales, it is a relatively small player. A supermassive black hole can also be quiet, but when it becomes active, it can dominate its entire galaxy. As it feeds on surrounding matter, it can release enormous amounts of energy, creating bright quasars and launching powerful jets that stretch across vast distances. These outbursts can heat gas, stop star formation, or reshape the galaxy itself. In this sense, supermassive black holes are not just passive objects, they are architects of cosmic structure. This big picture comparison sets up the core conflict of this video. On one side, we have stellar black holes, born from death, small in size, scattered throughout galaxies, living relatively simple lives. On the other side, we have supermassive black holes, ancient giants sitting at galactic centers, shaping the evolution of entire star systems. They share the same name and the same basic physics, but everything else about them feels different. As we move forward, we will dive deeper into each of these stories. We will see how stellar black holes are born from collapsing stars, and how supermassive black holes challenge our understanding of the early universe. We will explore how their sizes change the way gravity behaves near them, how their feeding habits differ, and how their influence spreads across space and time. For now, it is enough to recognize that when we say black hole, we are really talking about two giants with two very different stories. Understanding that difference is the key to understanding why black holes are not just fascinating objects, but essential pieces of the universe's grand design. The story of a stellar black hole does not begin with darkness, it begins with light. Brilliant, powerful, life-giving light. Long before a stellar black hole exists, there is a massive star burning fiercely in space, shining brighter and hotter than most stars we see in the night sky. These stars are not ordinary. They are giants, born with far more mass than stars like our Sun, and from the very beginning, their lives are intense, fast and dramatic. A massive star forms inside a huge cloud of gas and dust. Gravity slowly pulls this material together, compressing it until the pressure and temperature at the center become extreme. When the core becomes hot enough, nuclear fusion begins. Hydrogen atoms smash together to form helium, releasing enormous amounts of energy. This energy pushes outward, balancing gravity's inward pull. As long as this balance exists, the star remains stable. This balance is the reason stars shine and why they can live for millions or billions of years. For a massive star, life burns fast. The more massive the star, the harder gravity squeezes its core, and the faster nuclear fuel is consumed. While a small star like the Sun can live for billions of years, a massive star may live only a few million years. It shines brighter, burns hotter, and races through its fuel at an incredible pace. Inside the star, fusion continues step by step. Hydrogen turns into helium. Helium turns into heavier elements, like carbon and oxygen. Eventually, the star builds layers, like an onion, with different elements burning at different depths. But there is a limit to this process. Fusion produces energy only up to a certain point. When the core begins forming iron, the story changes. Iron is a dead end for fusion. Fusing iron does not release energy. Instead, it consumes energy. The moment iron builds up in the core, the star's engine begins to fail. The outward pressure that once balanced gravity weakens, and gravity starts to win. This moment marks the beginning of the end. The core of the star, no longer supported by fusion, collapses under its own enormous weight. This collapse happens incredibly fast in a fraction of a second. The core shrinks violently, and as it does, temperatures and pressures skyrocket. The outer layers of the star crash inward, then rebound off the suddenly rigid core. What follows is one of the most powerful events in the universe, a supernova explosion. A supernova is not just an explosion, it is a complete transformation. In a matter of seconds, the star releases more energy than it produced during its entire lifetime. The outer layers are blasted into space at incredible speeds, creating a glowing, expanding shell of gas and debris. For a brief time, the exploding star can shine brighter than an entire galaxy. Heavy elements are forged and scattered across space, becoming the building blocks for planets, life, and future stars. In this way, even destruction plays a creative role in the universe, but the real story of a stellar black hole lies at the center of this chaos. After the explosion, what remains depends entirely on the mass of the collapsing core. If the core is relatively small, it may form a neutron star, an object so dense that atoms are crushed together. But if the core is massive enough, even this extreme state is not enough to stop gravity. The collapse continues. When gravity overwhelms all known forces, the core collapses endlessly inward. There is no known pressure strong enough to halt it. Space itself bends around the collapsing mass and a black hole is born. The event horizon forms, sealing off the interior from the rest of the universe. From the outside, the core seems to disappear. From that moment on, the stellar black hole exists. This birth process explains why stellar black holes are relatively small compared to their supermassive cousins. They form from single stars, and even the largest stars have limits. Typically, a stellar black hole has a mass between about 3 and several dozen times the mass of our Sun. All that mass is compressed into a region only a few tens of kilometers across. To put this in perspective, a stellar black hole with the mass of 10 suns would have an event horizon roughly the size of a small city. That is astonishing when you consider the amount of matter involved. Despite their violent birth, stellar black holes often live quiet lives afterward. Once the explosion fades and the surrounding debris drifts away, the black hole becomes almost invisible. It does not glow. It does not announce its presence. It simply exists, following the same orbit around the galaxy that the original star once followed. In many cases, the stellar black hole is left alone, drifting through space without interacting with anything nearby. Sometimes, however, a stellar black hole is not alone. If the original star was part of a binary system, the black hole may still have a companion star orbiting nearby. In such systems, gravity can pull gas from the companion star toward the black hole. As this gas spirals inward, it heats up and emits powerful X-rays. These systems become some of the brightest X-ray sources in the sky. Once again, we see that black holes reveal themselves not by their darkness, but by the light produced around them. The dramatic birth of stellar black holes also explains why scientists are confident about their formation process. We observe massive stars. We observe supernova explosions. We observe compact objects left behind. We see the chain of events clearly. While many details are still being refined, the overall story fits well with what we know about stellar physics. Stellar black holes are the natural outcome of massive stars reaching the end of their lives. This clear origin sets stellar black holes apart. They are born from death. Their existence is tied to individual stars and their life cycles. Their mass range reflects the limits of stellar formation. Their size reflects extreme compression, not enormous mass. They are powerful, but their influence is local. Understanding this story is crucial because it gives us a baseline. Stellar black holes show us what gravity can do when a star collapses. They represent one extreme outcome of stellar evolution. But as dramatic as this process is, it still cannot explain the largest black holes in the universe. No single star, no matter how massive, can produce a black hole millions or billions of times heavier than the Sun. And that realization leads us forward. If stellar black holes are born from dying stars, then supermassive black holes must have a different origin entirely. Their story does not begin with one star's death, but with something far larger and far older. The death of a star shows us how black holes can form. The mystery of supermassive black holes will show us how much we still do not understand about the universe. If the birth of a stellar black hole feels dramatic, the birth of a supermassive black hole feels almost unbelievable. These objects do not simply stretch our imagination. They challenge our understanding of how the universe itself came together. Supermassive black holes are not rare curiosities found in a few special places. They appear to exist at the center of almost every large galaxy we observe, including our own Milky Way. Quiet or active, hidden or blazing as quasars, they sit at the gravitational heart of galaxies, influencing the motion of billions of stars. And yet, unlike stellar black holes, their origin remains one of the greatest unsolved mysteries in modern science. The first striking fact about supermassive black holes is their location. They are almost always found at the center of galaxies. This is not a coincidence. When astronomers track the motion of stars near galactic centers, they see stars orbiting an invisible but incredibly massive object. The only explanation that fits the data is a supermassive black hole. These black holes are not drifting through space. They are anchored, deeply embedded in the structure of the galaxy itself. This alone suggests that their story is tightly linked to the story of galaxies. Then comes the problem of size. A supermassive black hole is not just a little bigger than a stellar black hole. It is millions to billions of times more massive than our Sun. To put this into perspective, even the largest stars ever known are only a few hundred times the mass of the Sun. No star, no matter how extreme, can collapse into something that massive. Even if many stars died and merged together, the numbers still do not add up easily. The idea that supermassive black holes are simply grown-up stellar black holes quickly runs into serious problems. One of the biggest problems is time. When astronomers look deep into space, they are also looking back in time. Some supermassive black holes are observed when the universe was very young, less than 1 billion years old. These black holes are already enormous at that early stage, sometimes billions of times the mass of the Sun. The question becomes unavoidable. How did they grow so big so fast? Stellar black holes grow slowly. They need time to pull in matter, and there are natural limits to how quickly that can happen. The early universe simply does not seem to give them enough time. This creates what scientists often call the early universe problem. The universe began in a hot, dense state. Over time, matter cooled, stars formed, and galaxies slowly assembled. Stellar black holes form after massive stars live and die, which itself takes time. But supermassive black holes appear too early, already fully formed, already massive, already shaping galaxies. It is as if they were present before galaxies were fully built, raising the possibility that galaxies formed around black holes, not the other way around. Because normal star death cannot explain their size and timing, scientists have proposed several competing theories for how supermassive black holes might form. Each theory tries to solve the same puzzle but approaches it from a different angle. None has been fully proven, and all are still debated. One idea is that supermassive black holes began as smaller seed black holes. These seeds could have formed from the collapse of the very first generation of stars in the universe, stars that were much larger than most stars today. These early stars, sometimes called primordial or population 3 stars, may have been hundreds of times more massive than the Sun. When they died, they could have left behind black holes larger than typical stellar black holes today. Over time, these seeds could grow by pulling in gas and merging with other black holes. This idea sounds reasonable, but it still struggles with time. Even starting with large seeds, growing to billions of solar masses so quickly is difficult. Another idea is direct collapse. In this scenario, instead of forming stars first, enormous clouds of gas in the early universe collapsed directly into black holes. These gas clouds would have been so massive and so hot that they never fragmented into individual stars. Instead, gravity pulled the entire cloud inward, forming a black hole thousands or even millions of times the mass of the Sun in one step. This would solve the time problem by skipping the star phase entirely. However, this process requires very specific conditions, and scientists are still debating whether those conditions were common enough in the early universe. A third possibility involves runaway growth in dense environments. In the crowded centers of young galaxies, black holes and stars could collide and merge repeatedly. This chain reaction could rapidly build up mass. But again, simulations show that this process may not be efficient enough to explain the largest supermassive black holes we observe so early. There are also more speculative ideas. Some researchers explore whether black holes could form directly from fluctuations in the early universe itself, long before stars existed. Others examine exotic physics that might allow faster growth than we currently understand. These ideas push the boundaries of known science and are treated with caution, but they show just how open this question remains. What makes this mystery even more fascinating is the close relationship between supermassive black holes and their host galaxies. Observations show that the mass of a supermassive black hole is often linked to the mass of the galaxy's central bulge. This suggests a deep connection. As galaxies grow, their central black holes grow. As black holes become active, they release energy that can slow or stop star formation in the galaxy. This feedback loop hints that supermassive black holes are not just passengers inside galaxies. They are partners in galaxy evolution. Despite decades of research, scientists still argue about which formation path is correct. Part of the challenge is that we cannot watch supermassive black holes being born directly. Their formation happened billions of years ago, far beyond the reach of direct observation. We must rely on indirect evidence, computer simulations, and observations of distant galaxies that show us snapshots of the early universe. This uncertainty is not a weakness of science. It is a sign that we are standing at the edge of what we know. Supermassive black holes sit at the intersection of gravity, galaxy formation, and the early universe. Understanding how they formed would answer multiple questions at once. It would tell us how the first galaxies assembled. It would reveal how matter behaved under extreme conditions. It might even point toward new physics. For now, the birth of supermassive black holes remains an open story. We know where they are. We know how massive they are. We know they play a central role in shaping galaxies, but we do not yet know exactly how they came to be. That mystery is part of what makes them so compelling. Stellar black holes show us what happens when a star dies. Supermassive black holes ask a deeper question. What happens when the universe itself begins to organize on the largest scales? As we move forward, this mystery will continue to guide our exploration. Each new telescope, each deeper look into the early universe brings us closer to an answer. Until then, supermassive black holes remain one of the universe's greatest unanswered questions. Silent giants whose origins are still written in the language of cosmic mystery. If there is one part of the black hole story that truly breaks the human mind, it is size. Not power, not gravity, size, because when we hear the word black hole, our brain tends to imagine one vague object, just bigger or smaller. But the difference in size between stellar black holes and supermassive black holes is so extreme that it almost feels like we're talking about two completely different kinds of reality. This difference is not just large, it is overwhelming. Let's begin with a stellar black hole. These black holes are born from massive stars, and despite their terrifying reputation, they are surprisingly small. A typical stellar black hole might have the mass of 10 suns. That sounds enormous, and it is, but here is where intuition fails. All that mass is compressed into a region only a few tens of kilometers across. Not thousands, not millions, tens. To make this real, imagine Earth. Earth has a diameter of about 12,000 kilometers. Now imagine shrinking Earth down until it is smaller than a city. That is closer to the size of a stellar black hole's event horizon. If a stellar black hole were placed on Earth's surface, it would not tower over mountains or stretch across continents. It would be smaller than most cities. You could walk across the entire event horizon in a short drive, if such a thing were possible. And yet, that tiny region would contain more mass than multiple suns combined. This is where the shock begins. Something so small, yet so massive, feels impossible. Our brains are not built to understand density at this level. A stellar black hole packs the mass of a star into a space barely larger than a neighborhood. That compression is what gives it such intense gravity near its surface. The closer you get, the stronger the pull becomes, extremely fast. Now let's shift our attention to supermassive black holes. If stellar black holes surprise you, supermassive black holes completely destroy any remaining sense of scale. These black holes are not city-sized. They are solar system-sized, and sometimes much larger. A supermassive black hole with a mass millions of times that of the Sun has an event horizon that can stretch wider than the orbit of Mercury or Venus. More massive ones can extend beyond the orbit of Earth. The largest known supermassive black holes have event horizons so vast that the entire solar system, from the Sun out past Neptune, could fit inside them comfortably. In some cases, the event horizon is larger than the distance between the Sun and Pluto. Think about that for a moment. A stellar black hole could hide inside a city. A supermassive black hole could swallow the solar system not because it is aggressive, but simply because it is that large. The difference is not gradual, it is extreme. We are not talking about something being 10 times bigger or 100 times bigger. We are talking about millions or billions of times more mass and event horizons that span astronomical distances. This size difference directly affects the event horizon. The event horizon is the boundary where escape becomes impossible, and its size depends entirely on mass. A small black hole has a small event horizon. A massive black hole has a huge one. This means the point of no return is very close to the center for stellar black holes and incredibly far out for supermassive ones. This leads to one of the most counterintuitive facts about black holes. Bigger does not always mean more dangerous at the edge. Near a stellar black hole, gravity changes extremely rapidly over short distances. This creates powerful tidal forces that can stretch and tear objects apart long before they reach the event horizon. Near a supermassive black hole, gravity changes much more gently across space. The pull is still immense, but it is spread over a much larger area. In simple terms, a stellar black hole is like falling toward a sharp cliff. The change is sudden and violent. A supermassive black hole is more like descending a long, smooth slope. The total drop is far greater, but the slope near the edge can feel surprisingly gentle. This is why, in theory, something could cross the event horizon of a supermassive black hole without immediately being torn apart, while the same would not be true near a stellar black hole. This brings us to density, another concept that often confuses people. It feels natural to assume that the bigger black hole must also be denser, but this is not true. Density depends on how much mass is packed into a given volume. While supermassive black holes have far more mass, their volume grows even faster. As a result, the average density inside the event horizon of a supermassive black hole can actually be lower than that of a stellar black hole. In some cases, it can even be lower than water. This idea feels wrong at first. How can something that powerful be less dense? The answer lies in scale. When mass increases, the event horizon grows in size, spreading that mass over a much larger region. Stellar black holes cram a few suns into a tiny space. Supermassive black holes spread billions of suns across an enormous region. Both trap light, both are black holes, but their internal packing is very different. Visual storytelling is essential here because numbers alone fail us. Saying millions of solar masses or tens of kilometers does not truly register. What matters is comparison. A stellar black hole compared to Earth is like a grain of sand compared to a stadium, yet heavier than the entire stadium combined. A supermassive black hole compared to the solar system is like replacing the Sun with an invisible giant that quietly anchors everything around it. This scale difference also explains why these two types of black holes live such different lives. Stellar black holes are compact and local. Their influence is intense but limited to nearby space. Supermassive black holes are vast and central. Their influence stretches across entire galaxies. The same physical rules apply, but the outcome feels completely different because of size alone. When we compare these objects side by side, the universe stops feeling intuitive. How can two things be called by the same name when one could hide in a city and the other could swallow planets? The answer is that black holes are defined not by size but by a condition. When gravity becomes strong enough that escape is impossible beyond a certain boundary, a black hole exists. Everything else is scale. This is why size comparison is not just a fun fact. It is the key to understanding everything that follows. Feeding behavior, energy output, time effects, and even the experience of falling in all depend on size. Stellar black holes and supermassive black holes are built from the same blueprint, but one is written in small print and the other in bold letters across the universe. Once you truly grasp this scale, you begin to see why scientists treat these black holes as separate characters in the cosmic story. One is compact, violent, and born from death. The other is vast, ancient, and tied to the rise of galaxies themselves. Same name, same physics, completely different worlds. And this realization prepares us for what comes next. Because size does not just affect appearance, it affects how black holes eat, how they shine, how they influence their surroundings, and how they shape the universe over billions of years. The difference in size is not just big, it is mind-breaking. When people talk about black holes, they often mix up two ideas without realizing it: mass and size. These words feel similar in everyday life, but in the universe of black holes, they describe very different things. Understanding this difference is essential, because mass is the true source of a black hole's power, while size is only a result of how that mass bends space. Once this becomes clear, the strange behavior of black holes starts to make sense. Mass is simply how much matter an object contains. Size is how much space that matter occupies. In our daily experience, these two usually grow together. A truck is bigger and heavier than a bicycle. A mountain is larger and heavier than a house. Our brains learn to connect size with weight. Black holes break this connection completely. A stellar black hole can have the mass of 10 suns but be smaller than a city. A supermassive black hole can have the mass of 1 billion suns and yet be spread across a region larger than the solar system. Both are incredibly heavy. Both bend space and time. But the way their mass is distributed creates very different gravitational experiences. Let's start with stellar black holes. These are the smaller members of the black hole family. But small here is misleading. Stellar black holes usually contain between about 3 and several dozen times the mass of our Sun. That means if you could somehow put 10 suns on a scale, a typical stellar black hole would weigh about the same. But instead of spreading that mass across a star millions of kilometers wide, it is crushed into a region only a few tens of kilometers across. This extreme compression is why gravity near a stellar black hole becomes so intense. The closer you get, the faster gravity increases. Space itself is sharply curved. This sharp curvature creates enormous tidal forces, meaning gravity pulls much harder on one part of an object than another. Near a stellar black hole, this difference becomes deadly very quickly. The mass may be only a few suns, but because it is packed so tightly, the gravitational effects are brutal at close range. Now let's move to supermassive black holes. These objects take the idea of mass and push it beyond anything familiar. Instead of weighing a few suns, they weigh millions or billions of suns. Imagine every star in a large galaxy, then imagine taking a fraction of that total mass and concentrating it into one object at the center. That is what a supermassive black hole represents. But here is the key difference. As mass increases, the size of the event horizon increases as well. The boundary where light can no longer escape moves farther out. This means that while a supermassive black hole has vastly more mass, that mass is spread across a much larger region of space. Gravity near the event horizon does not change as violently over short distances as it does near a stellar black hole. This leads to a surprising conclusion. Near the edge of a supermassive black hole, gravity can actually feel gentler than near a stellar black hole. The total gravitational pull is enormous, but the gradient, the change in strength across space, is smoother. This is why size does not directly translate into danger. Bigger black holes are not automatically more destructive at their edges. To understand this without equations, imagine stretching a rubber sheet. A stellar black hole is like placing a heavy metal ball on a very small rubber sheet. The dip is steep and sharp. A supermassive black hole is like placing a massive weight on an enormous rubber sheet. The dip is deep, but it slopes gently near the edges. Both curve the sheet, but in very different ways. This difference in curvature explains why the experience near these black holes differs so much. Near a stellar black hole, gravity changes rapidly, tearing objects apart long before they reach the event horizon. Near a supermassive black hole, gravity changes more gradually, allowing objects to approach much closer before extreme effects occur. Yet both outcomes come from the same underlying rule. Gravity responds to mass. It is also important to understand that mass determines how black holes grow. Stellar black holes usually gain mass slowly. They may pull gas from a nearby star or merge with another black hole, but these events are relatively rare. Their growth is limited by their environment. Even over billions of years, a stellar black hole does not typically grow into a supermassive one. Supermassive black holes, on the other hand, live in the most crowded and resource-rich regions of galaxies. Gas clouds, stars, and even other black holes pass near them. Over cosmic time, this allows them to grow dramatically. Their enormous mass makes them gravitational anchors, pulling material inward from vast distances. But even here, growth is not unlimited. The process is regulated by energy released as matter falls in, which can push surrounding material away. Despite these differences, one fact remains constant. Both stellar and supermassive black holes follow the same fundamental laws of physics. There is no special rule for giant black holes and another rule for small ones. Gravity behaves the same way everywhere. The equations that describe how space bends around a stellar black hole also describe how it bends around a supermassive one. The difference lies entirely in scale. This is a powerful idea. It means the universe does not need separate explanations for different kinds of black holes. One simple set of rules, applied at different scales, produces wildly different outcomes. A few suns packed into a tiny region create a violent, compact object. Billions of suns spread across a vast region create a quiet giant that controls an entire galaxy. Understanding mass also helps explain why black holes do not behave like monsters. A supermassive black hole does not pull stars inward, simply because it is heavy. Stars orbit it just as planets orbit the sun, responding to gravity in predictable ways. Only when something loses enough energy or wanders too close does it begin to fall in. Gravity is not a trap. It is a rule. In many ways, mass is the true identity of a black hole. Size is just how far that identity extends into space. A stellar black hole announces its presence only when something comes very close. A supermassive black hole announces its presence through the motion of entire star systems. Both are heavy beyond comprehension. Both shape their surroundings through gravity alone. This understanding also sets the stage for the next chapters of the story. How black holes eat, how they shine, how they influence galaxies. All of these behaviors trace back to mass, not mystery, not magic, just mass interacting with space and time in the most extreme way nature allows. When we strip away the fear and the fiction, what remains is something even more impressive. Black holes are not strange because they break the rules. They are strange because they obey the rules perfectly, even when those rules are pushed to their absolute limits. To truly understand black holes, it is not enough to know how big or heavy they are. We must also understand where they live. Location shapes behavior, influence, and destiny. In the universe, stellar black holes and supermassive black holes occupy very different neighborhoods, and those locations explain much of how they behave and why they matter. Once you see where each type lives, the universe starts to look less chaotic and more structured, as if black holes are placed exactly where gravity needs them most. Stellar black holes are scattered throughout galaxies, much like stars themselves. This makes sense because stellar black holes are born from stars. When a massive star dies and collapses, the black hole that forms inherits the star's original position and motion. If the star was orbiting the galaxy, the black hole continues that same orbit. It does not suddenly fall to the center. It does not become special in terms of location. It becomes a dark, compact traveler embedded within the galaxy's disk, halo, or spiral arms. Because of this, stellar black holes are everywhere, but almost all of them are invisible. Our galaxy alone is thought to contain millions of stellar black holes, quietly moving through space, alongside stars, gas clouds, and planets. Most of them never interact with anything closely enough to reveal themselves. They do not glow. They do not announce their presence. They're gravitational ghosts, following predictable paths around the galactic center, just like stars do. Some stellar black holes exist alone. Others remain in binary systems, orbiting a companion star. These systems give astronomers rare opportunities to detect them, because the black hole's gravity pulls matter from the nearby star, creating bright emissions. But even then, their influence remains local. A stellar black hole affects its immediate surroundings, not the galaxy as a whole. It is a resident, not a ruler. Supermassive black holes, in contrast, do not wander. They are anchored. They live at the exact centers of galaxies where gravity collects matter most efficiently. These black holes are not scattered randomly. Their location is precise and meaningful. At the heart of a galaxy, stars orbit a central point, and at that point sits a supermassive black hole. This central placement is not accidental. In the early universe, matter flowed along invisible structures called cosmic filaments. Gas collected in dense regions, forming the seeds of galaxies. The densest point naturally became the center. This is where gravity was strongest, where matter gathered fastest, and where a central black hole could grow. Over billions of years, as galaxies merged and evolved, their central black holes merged as well, reinforcing the idea that galaxies and supermassive black holes grow together. One of the most striking discoveries in modern astronomy is that almost every large galaxy appears to host a supermassive black hole at its center. Spiral galaxies, elliptical galaxies, even some irregular ones, all show evidence of a massive central object. The sizes of these black holes vary, but their presence is nearly universal. This tells us something profound. Supermassive black holes are not rare accidents. They are standard components of galaxy formation. Even more remarkable is the relationship between the mass of a galaxy and the mass of its central black hole. Observations show a strong link between the two. Bigger galaxies tend to have bigger central black holes. This connection suggests a deep feedback relationship. As the galaxy grows, the black hole grows. As the black hole becomes active, it can release energy that affects the galaxy's gas, slowing or shaping star formation. Neither evolves in isolation. This relationship changes how we think about galaxies. A galaxy is not just a collection of stars with a black hole sitting quietly in the middle. It is a dynamic system where the central black hole plays a regulating role. When gas falls toward the center and feeds the black hole, the energy released can heat surrounding gas, preventing it from forming new stars. When the black hole is quiet, star formation can resume. Over time, this balance helps shape the size, structure, and lifespan of the galaxy itself. Stellar black holes do not have this role. No matter how powerful they are locally, they cannot influence star formation across thousands of light years. Their gravity fades quickly with distance. Supermassive black holes, by contrast, influence the behavior of matter across entire galactic cores. Their reach is not because they pull everything in, but because their energy output and gravitational stability affect how galaxies organize themselves. This brings us to an intriguing question. What would happen if a galaxy lost its central supermassive black hole? The answer is surprising. The galaxy would not instantly fall apart. Stars do not orbit the black hole directly. They orbit the combined mass of the galaxy. Removing the central black hole would not cause stars to fly off or collapse inward overnight. On short timescales, the galaxy would look much the same, but over long timescales, the absence of a central black hole would matter. The delicate balance between gas cooling and heating would change. The feedback processes that regulate star formation would weaken. The galaxy's central structure could evolve differently, potentially becoming denser or more chaotic. The black hole acts less like a gravitational anchor and more like a regulator, keeping the galaxy's growth in check. This difference in role highlights why location matters so much. Stellar black holes are products of galaxies. Supermassive black holes are partners in building galaxies. One lives within the system. The other helps define the system. It also explains why scientists study galactic centers so intensely. By watching stars orbit the invisible core, astronomers can measure the mass of the central black hole with extraordinary precision. These observations have provided some of the strongest evidence that supermassive black holes exist at all. In our own galaxy, stars near the center move so fast and in such tight orbits that only a supermassive black hole can explain their motion. In the end, where black holes live tells us who they are. Stellar black holes are scattered survivors of stellar death, quietly orbiting within galaxies like dark remnants of past explosions. Supermassive black holes are ancient giants sitting at the heart of galaxies, shaping their evolution across billions of years. Same physics, same fundamental rules, completely different cosmic addresses. Understanding this spatial difference prepares us for the next chapters of the story, because where black holes live determines how they eat, how they shine, and how loudly they announce their presence to the universe. Location is not a detail, it is destiny. Few ideas about black holes cause more fear and confusion than the idea of feeding. The phrase "black hole eats everything" has become so common that many people imagine black holes as cosmic predators, endlessly swallowing stars, planets, and entire galaxies. This image feels dramatic, but it is wrong in a very important way. Black holes do not eat the universe. They are actually surprisingly slow, selective, and often very quiet eaters. To understand why, we need to understand accretion, the simple and natural process by which black holes grow. Accretion is not a violent snap or a sudden gulp. It is a gradual process, more like water slowly circling a drain than a monster pulling everything inward. A black hole cannot grab something from far away just because it exists. Matter has to lose energy and move close enough for gravity to take over. Most matter in the universe never does. The key structure involved in feeding is the accretion disk. Imagine pouring honey into a bowl. Instead of falling straight down, it swirls around, forming a spiral as it moves inward. The same thing happens around a black hole. Gas, dust, or even stars that wander too close usually have sideways motion. Instead of falling directly in, they begin to orbit. As more material joins in, it forms a flat, spinning disk around the black hole. This disk is the accretion disk. The accretion disk is not part of the black hole itself. It is outside the event horizon. The black hole remains invisible, but the disk can become incredibly bright. As matter spirals inward, friction causes particles to rub against each other. This friction heats the material to extreme temperatures. Hot gas glows. The faster it moves and the closer it gets, the hotter and brighter it becomes. In many cases, the light from the accretion disk is the brightest thing in the entire galaxy. This simple picture already removes a major fear. Black holes do not instantly swallow things. Matter has to spiral in slowly, shedding energy bit by bit. This process can take thousands, millions, or even billions of years. Even when a black hole is actively feeding, it is not eating everything around it. It is eating what happens to fall close enough and lose enough energy to stay trapped. Now let's compare how stellar black holes and supermassive black holes feed, because the differences are dramatic. A stellar black hole usually feeds only if it has a nearby source of material. Most stellar black holes are isolated. There is nothing close enough for them to pull in. In these cases, they're completely dark and silent. They do not glow. They do not grow. They simply orbit the galaxy, unchanged for millions of years. When a stellar black hole does feed, it is often because it has a companion star. In a binary system, the black hole's gravity can pull gas from the outer layers of the star. This gas forms an accretion disk around the black hole and heats up as it spirals inward. These systems can shine strongly in X-rays and are among the easiest stellar black holes to detect. But even here, the feeding is limited. The black hole can only pull material at a certain rate, and the companion star often survives for a long time. Supermassive black holes feed in a very different environment. Sitting at the center of a galaxy, they are surrounded by enormous reservoirs of gas and dust. In principle, this gives them access to far more material. But even then, feeding is not constant. In fact, most supermassive black holes are quiet most of the time. This surprises many people. If supermassive black holes are so massive and sit at the center of galaxies, why are they not always active? The answer lies in angular momentum, the tendency of matter to keep moving sideways. Gas in galaxies does not fall straight in, it orbits. For gas to reach the black hole, it must lose energy and angular momentum. This is not easy. It requires interactions, collisions, and disturbances. Events like galaxy mergers, close encounters, or internal instabilities can push gas toward the center. When this happens, the supermassive black hole can suddenly become active, forming a bright accretion disk and sometimes launching powerful jets. These periods create quasars, some of the brightest objects in the universe, but they are temporary. Once the nearby gas is used up or blown away, the black hole becomes quiet again. This is why a supermassive black hole can spend billions of years barely eating at all. It is not because it is weak. It is because feeding depends on supply and conditions. Without gas falling inward, even the largest black hole remains dormant. Feeding speed also differs greatly between the two types. Stellar black holes grow slowly. Even in the best conditions, they gain mass at a modest rate. Supermassive black holes can grow faster when conditions are right, but even they have limits. If too much matter falls in too quickly, the energy released can push surrounding gas away, cutting off the food supply. In this sense, black holes regulate their own growth. Stars also play a role in feeding, but not in the dramatic way often imagined. Stars are dense and compact. They do not usually fall into black holes. Occasionally, a star may wander too close to a supermassive black hole and be torn apart in a tidal disruption event. The gas from the shredded star forms an accretion disk and briefly feeds the black hole. These events are rare. They are flashes, not the normal diet. Most of the time, black holes feed on gas and dust, not whole stars. This slow, steady feeding shapes their growth over cosmic time. It also explains why black holes are not immediate threats to their surroundings. Gravity does not act like a vacuum cleaner. It acts like a well. Objects fall in only if they are already moving in the wrong direction and lose enough energy. Understanding accretion changes how we think about black holes. They are not destroyers chasing matter. They are passive objects responding to what comes close. Feeding depends on environment, motion, and time. A stellar black hole may never feed at all. A supermassive black hole may alternate between long periods of silence and short periods of intense activity. This also helps explain why black holes are so important to astronomy. The light from accretion disks allows us to study them indirectly. Without feeding, black holes would be almost impossible to detect. Ironically, black holes teach us about the universe not when they're dark, but when they're eating. Once fear is replaced with understanding, the picture becomes clearer. Accretion is not chaos. It is a slow, ordered process, shaped by gravity and motion. Stellar and supermassive black holes eat in different ways, at different speeds, and with different consequences. But both follow the same simple rule. They grow only when the universe gives them something to grow on. And that simple rule sets the stage for the next part of the story. Because when black holes do feed, the energy they release can be enormous. Sometimes that energy does more than light up space. Sometimes it reshapes entire galaxies. When people hear that light cannot escape a black hole, they often assume that black holes must be powerless, silent objects hidden in darkness. This assumption could not be further from the truth. In reality, black holes are among the most powerful engines in the universe, not because of what escapes from inside them, but because of what happens just outside their boundaries. The greatest influence of black holes comes not from swallowing matter, but from how violently they transform matter before it disappears. This is where energy output becomes the real story. Black holes themselves do not emit light, but the process of matter falling towards them can release more energy than almost anything else known in nature. And once again, the difference between stellar black holes and supermassive black holes is not just one of scale, but of cosmic impact. Let's begin with stellar black holes. On their own, stellar black holes are dark and quiet. They produce no light and very little detectable signal. But when a stellar black hole exists in a binary system with a normal star, everything changes. These systems are known as X-ray binaries, and they are some of the most energetic objects in the sky. In an X-ray binary, the stellar black hole pulls gas from its companion star. This gas does not fall straight in. It spirals, forming an accretion disk. As the gas moves faster and faster, it heats up to millions of degrees. At these temperatures, the disk emits powerful X-rays. These X-rays can be detected from across the galaxy, making stellar black holes visible despite their darkness. What is remarkable is how efficient this process is. A stellar black hole converting matter into energy through accretion can release far more energy per unit mass than nuclear fusion inside stars. The same amount of matter falling into a black hole can produce many times more energy than that matter could ever produce by shining as a star. This makes black holes incredibly efficient engines. Despite this efficiency, the influence of stellar black holes remains local. An X-ray binary can affect its nearby environment, heating surrounding gas and producing intense radiation. But its reach is limited. It does not reshape galaxies. It does not regulate star formation on large scales. Its power is impressive, but contained. Supermassive black holes operate on a completely different level. When a supermassive black hole becomes active, the energy released can rival or exceed the combined light of billions of stars. These active periods create quasars, some of the brightest objects in the observable universe. A quasar is not a special type of black hole. It is a phase. It is what happens when a supermassive black hole is feeding rapidly. In a quasar, the accretion disk becomes intensely luminous. Gas swirling near the event horizon reaches extreme temperatures, releasing enormous amounts of radiation across the electromagnetic spectrum. From radio waves to visible light to X-rays, quasars blaze across space. They can be seen from billions of light years away, allowing astronomers to study the early universe. But radiation is only part of the story. Some of the most dramatic displays of black hole power come in the form of jets. These are narrow beams of particles launched from regions near the black hole at speeds close to the speed of light. Jets can stretch far beyond the galaxy itself, reaching distances measured in hundreds of thousands or even millions of light years. The exact mechanism that produces jets is still being studied, but strong magnetic fields and rapid rotation play key roles. What matters for our story is their effect. Jets carry enormous energy outward, ploughing through surrounding gas. They heat it, compress it, and sometimes blow it away entirely, In doing so, jets can shut down star formation by preventing gas from cooling and collapsing into new stars. This is where black holes begin to shape galaxies. For a long time, scientists assumed that galaxies controlled black holes, not the other way around. But evidence now shows that supermassive black holes can control their host galaxies in profound ways. When a central black hole becomes active, its energy output can regulate how many new stars form. This process is called feedback. Feedback works like this. Gas in a galaxy cools and collapses to form stars. But if a supermassive black hole heats that gas or pushes it away, star formation slows or stops. Over billions of years, this regulation helps explain why galaxies look the way they do. It explains why some galaxies stop forming stars and become quiet, while others continue forming stars for much longer. This influence extends far beyond the black hole's immediate neighborhood. The black hole itself may be small compared to the galaxy, but its energy output reaches across vast distances. Once again, size alone does not determine power. Location and energy flow matter more. Stellar black holes cannot do this. Even though they are efficient energy producers, they do not have access to enough material or influence over enough space. Their power is intense but narrow. Supermassive black holes are powerful because they sit at the crossroads of galactic motion and matter flow. All of this leads to a fascinating paradox. Black holes are defined by the fact that light cannot escape them, yet they are responsible for some of the brightest phenomena in the universe. The key is understanding that the light comes from outside the event horizon. The black hole itself remains dark. The universe lights up around it. This distinction helps remove confusion. Black holes do not shine. Accretion shines, jets shine, heated gas shines. The black hole is the cause but not the source of light. Its gravity sets the stage for energy release, but the energy comes from matter losing gravitational potential as it falls inward. Another important point is that this power is not constant. Black holes are not always active. A supermassive black hole can switch between quiet and violent phases over cosmic time. During quiet periods, it may have little effect on its galaxy. During active periods, it can dominate the galaxy's evolution. This on and off behavior is part of what makes black holes such complex players in cosmic history. When we compare stellar and supermassive black holes in terms of energy output, the contrast becomes clear. Stellar black holes demonstrate how powerful accretion can be on small scales. Supermassive black holes demonstrate how that same process, scaled up and placed at a galaxy's center, can influence the universe itself. This is the deeper lesson of black hole power. It is not about destruction. It is about transformation. Matter falling toward a black hole releases energy that reshapes space, heats gas, launches jets, and regulates star formation. Black holes do not create energy from nothing. They convert gravity into influence. By understanding this, we see black holes not as cosmic villains, but as engines of structure. They are dark at their core, yet luminous in their effects. They hide their centers, yet announce their presence across the universe. And whether small or vast, stellar or supermassive, their true power lies not in what they consume, but in what they change around them. To understand black holes fully, we must stop thinking in human time. Seconds, years, even centuries mean almost nothing on the cosmic clock. Black holes live on timescales so vast that they stretch our sense of history itself. And this is where one of the deepest emotional contrasts between stellar black holes and supermassive black holes appears. One type is still being born today, in violent flashes of death and rebirth. The other type is ancient, already old when galaxies were young, carrying a memory of the universe's earliest chapters. They are not just different in size, they are different in age, rhythm, and role in cosmic time. Stellar black holes belong to the present. Even today, somewhere in the universe, massive stars are reaching the end of their lives. They burn through their fuel, their cores collapse, and supernova explosions light up space. When the dust settles, a stellar black hole may remain. This process is ongoing. It has happened in the past, it is happening now, and it will continue to happen far into the future, as long as massive stars exist. This makes stellar black holes feel almost familiar, in a cosmic sense. They are part of the ongoing cycle of stellar life and death. A massive star forms, shines, explodes, and leaves behind a compact remnant. In some cases, that remnant is a black hole. These black holes are not ancient relics. They are products of recent events, at least on astronomical timescales. Some stellar black holes in our own galaxy may be only a few million years old, which is young compared to the age of the universe. Because stellar black holes form from stars, their formation rate depends on star formation. When galaxies actively form massive stars, they also create stellar black holes. When star formation slows, fewer new stellar black holes appear. This ties their existence closely to the current state of galaxies. They rise and fall with stellar populations, living fast, localized lives. Supermassive black holes tell a very different story. When astronomers look deep into space, they are also looking back in time. Light from distant galaxies takes billions of years to reach us. Some of the most distant objects we observe are quasars, powered by supermassive black holes. These quasars existed when the universe was less than 1 billion years old. That means supermassive black holes were already massive, already active, and already shaping galaxies at a time when the universe itself was still young. This creates a powerful emotional contrast. Stellar black holes are still being born today. Supermassive black holes seem to have been born long ago, near the dawn of cosmic structure. They are ancient monsters, not in a frightening sense, but in a deeply historical one. They have watched galaxies form, collide, and evolve over billions of years. This difference in age matters because it affects how we understand their growth. Stellar black holes begin small and usually stay small. They may gain a little mass by feeding or merging, but their growth is limited by environment and opportunity. Even over billions of years, a stellar black hole rarely grows beyond a few dozen times the mass of the Sun. Its life is defined by constraints. Supermassive black holes, by contrast, grow over enormous spans of time. They may begin as seeds, but over billions of years they pull in gas, merge with other black holes, and increase their mass dramatically. Each galaxy merger can bring two central black holes together, eventually forming a larger one. Each active feeding phase adds more mass. Their growth is slow but relentless, shaped by the evolution of the universe itself. This long growth history explains why age matters so much in understanding supermassive black holes. When we observe one today, we are seeing the result of billions of years of cosmic events layered on top of one another. Its mass is a record of past mergers, feeding episodes, and galaxy interactions. In a sense, a supermassive black hole is a fossil, preserving information about the history of its host galaxy. Time also explains why supermassive black holes are not always active. Over billions of years, galaxies go through quiet periods and violent periods. Gas supplies change, mergers happen, star formation rises and falls. The black hole responds to these changes. It may shine brightly as a quasar for a relatively short time, then fade into near silence for billions of years. These active phases are brief compared to the black hole's full lifespan, like flashes in an otherwise long, quiet existence. Stellar black holes experience time differently. Their lives are not shaped by galaxy mergers or cosmic evolution on the largest scales. They respond to local events. A nearby star drifts too close. A binary system evolves. Gas becomes available. Their activity is episodic and personal, not cosmic. They do not carry the memory of the early universe. They carry the memory of a single star's death. This contrast adds emotional depth to the story of black holes. Stellar black holes remind us that the universe is still alive, still changing, still producing extreme objects today. Supermassive black holes remind us that the universe has a deep past, filled with events so ancient that they shaped everything we see now. But cosmic time also helps us understand why these two types of black holes feel so different in character. Stellar black holes feel sharp and sudden. They are born in explosions. Their influence is immediate but limited. Supermassive black holes feel slow and inevitable. They grow patiently, shaping galaxies across unimaginable spans of time. When we step back and view black holes through the lens of cosmic time, fear gives way to perspective. These objects are not threats looming over humanity. They are participants in a story that began long before Earth existed and will continue long after our sun is gone. Stellar black holes mark moments. Supermassive black holes mark eras. This perspective changes how we think about the universe itself. The universe is not static. It has a history, a present, and a future. Black holes are woven into that timeline. Some are newborns, some are elders. All of them reflect the passage of cosmic time in their own way. As we move forward in this story, this understanding becomes crucial. To understand how black holes influence galaxies, how they test physics, and how they might one day fade away, we must remember their age. Time is not just a background detail. It is a defining feature of who these black holes are. Stellar black holes remind us that creation and destruction are still happening now. Supermassive black holes remind us that the universe remembers its beginnings. Together, they show us that black holes are not just objects in space, but chapters in a story that spans the entire age of the cosmos. One of the most common and reasonable questions people ask is simple and honest. If black holes do not emit light, how do scientists know they exist at all? This question is important because trust in science does not come from mystery or authority. It comes from understanding how evidence is gathered. Black holes are a perfect example of how science works when direct observation is impossible. We do not see black holes the way we see stars or planets. Instead, we detect them indirectly, by carefully observing how they affect the universe around them. Indirect observation means learning about something by its influence rather than by direct sight. We do this all the time in everyday life. We do not see the wind, but we see trees bending and leaves moving. We do not see gravity, but we see objects fall. In the same way, scientists do not see black holes directly, but they see how black holes bend light, move stars, heat gas, and shape entire galaxies. These effects are measurable, repeatable, and consistent with physical laws. Let's start with stellar black holes. Because they're relatively small and scattered throughout galaxies, they're difficult to detect. Most stellar black holes are completely invisible. They sit quietly in space doing nothing dramatic. If a stellar black hole is isolated, with no nearby matter falling into it, there is almost no way to detect it with current technology. This is why astronomers believe there are millions of stellar black holes in our galaxy that we have never seen. The situation changes when a stellar black hole has a companion star. In a binary system, two objects orbit each other due to gravity. If one of those objects is invisible, but very massive, its presence can still be detected by watching the motion of the visible star. This is one of the most powerful tools scientists use. Imagine watching a star that appears to be orbiting empty space. The star moves back and forth in a regular pattern, as if pulled by something unseen. By measuring the speed of this motion and the size of the orbit, scientists can calculate how much mass must be present to cause it. If the mass is too large to be a star and no light is coming from it, a black hole becomes the best explanation. This method is how many stellar black holes were first identified. The star acts like a visible marker, revealing the gravity of its invisible partner. When gas from the star is pulled toward the black hole and forms an accretion disk, the evidence becomes even stronger. The disk emits X-rays, which can be detected by space-based observatories. These X-rays fluctuate in ways that match predictions for matter spiraling into a black hole. X-ray observations are especially important because Earth's atmosphere blocks X-rays. To detect them, scientists use space telescopes designed specifically for high-energy light. These observatories allow astronomers to see energetic processes that are completely invisible to the human eye. When a stellar black hole feeds, it lights up the X-ray sky, announcing its presence clearly. Supermassive black holes are detected in a different way because they live in a different environment. They sit at the centers of galaxies, surrounded by countless stars. Instead of watching a single star in a binary system, scientists observe the motion of many stars near the galactic center. In the center of a galaxy, stars move extremely fast. By tracking their orbits over time, astronomers can map the gravitational field at the core. In some galaxies, stars orbit so quickly and so tightly around an invisible point that only an object with millions or billions of solar masses could explain their motion. No cluster of stars or gas could remain stable in such a small region without collapsing or glowing brightly. The only object that fits the data is a supermassive black hole. This method has been used with incredible precision in our own galaxy. By observing the paths of stars near the Milky Way's center over many years, scientists have measured the mass and location of the central black hole with astonishing accuracy. These observations leave very little room for alternative explanations. Another powerful detection method involves light itself. Even though black holes do not emit light, their gravity bends it. When light from a distant star or galaxy passes near a black hole, its path curves. This effect, known as gravitational lensing, can magnify, distort, or duplicate images of background objects. By studying these distortions, scientists can infer the presence and mass of invisible objects, including black holes. Supermassive black holes also reveal themselves during active phases. When they feed rapidly, their accretion disks shine brightly across the universe. Quasars, powered by supermassive black holes, are visible from billions of light years away. Their brightness, energy output, and variability match theoretical predictions of black hole accretion. No other known object can explain their properties as well. Jets provide another clue. Long, narrow beams of particles shooting from galactic centers are difficult to explain without a rotating supermassive black hole and strong magnetic fields. These jets interact with surrounding gas in ways that can be observed across enormous distances. Their structure and energy point directly back to a central black hole engine. Telescopes play a crucial role in all of this, but not all telescopes work the same way. Some observe visible light, others observe radio waves, infrared light, ultraviolet light, X-rays or gamma rays. Black hole detection requires a combination of these tools. Each type of light reveals a different piece of the puzzle. Radio telescopes can map jets and accretion disks. Infrared telescopes can peer through dust at galactic centers. X-ray observatories detect hot gas falling into black holes. Together, these instruments build a complete picture that no single observation could provide. This brings us to an important idea. Seeing in science does not always mean seeing with eyes. It means measuring effects, patterns, and changes. It means using instruments to extend human senses beyond their natural limits. Black holes remind us that reality is not limited to what we can directly perceive. The strongest evidence for black holes comes not from one observation, but from many independent lines of evidence pointing to the same conclusion. Star motions, X-ray emissions, gravitational lensing, jet behavior, and galaxy evolution all tell a consistent story. When different methods agree, confidence grows. This process also shows the strength of scientific thinking. Scientists do not declare the existence of black holes based on belief or imagination. They test predictions, they compare observations to models, they look for alternatives and rule them out. Over time, black holes remain the explanation that fits all the data best. Understanding how black holes are detected replaces mystery with clarity. These objects are not accepted because they are fascinating. They are accepted because the universe behaves exactly as it should if they exist. Their fingerprints are everywhere, written into the motion of stars and the glow of distant galaxies. In the end, black holes teach us a powerful lesson about knowledge. We do not need to see something directly to know it is real. We need evidence, consistency, and careful observation. Stellar black holes whisper their presence through nearby stars. Supermassive black holes announce themselves through the motion of entire galaxies. Both are unseen, yet undeniable. This trust in indirect observation is what allows science to explore the deepest and darkest corners of reality. Black holes may hide their centers, but they cannot hide their influence, and that influence tells us more than direct sight ever could. When people imagine getting close to a black hole, fear usually takes over. Images of instant destruction, violent tearing, and impossible chaos come to mind. But the real physics near a black hole is far more subtle, strange, and fascinating than frightening. It is not about sudden death. It is about extreme versions of familiar ideas, gravity, motion, and time, pushed to their absolute limits. To understand what really happens near a black hole, we need to slow down, replace fear with curiosity, and let the physics speak for itself. One of the most famous ideas associated with black holes is something called spaghettification. The name sounds humorous, and that is intentional. It helps soften a very extreme concept. Spaghettification describes what happens when an object gets close enough to a black hole that gravity pulls much harder on one part of it than another. This difference in gravitational pull is called a tidal force. Imagine holding a rubber band and pulling gently. It stretches a little, pull harder, and it stretches more. Near a black hole, gravity pulls much harder on the part of an object closer to the black hole than on the part farther away. Over time, this stretches the object lengthwise, while squeezing it sideways, turning it into a long, thin shape, like a strand of spaghetti. This is where the name comes from. But here is the important part. Spaghettification is not something that happens instantly, and it does not happen the same way near every black hole. Its strength depends heavily on the size of the black hole. This is one of the most surprising and misunderstood aspects of black hole physics. Near a stellar black hole, spaghettification is intense. Because stellar black holes are small and compact, gravity changes extremely rapidly over short distances. Even a small difference in position can mean a huge difference in gravitational pull. As a result, tidal forces become strong very quickly as you approach the black hole. Long before reaching the event horizon, an object would be stretched and torn apart. Near a supermassive black hole, the story is very different. Even though the total gravity is far stronger, the change in gravity across space is much gentler near the event horizon. This means tidal forces near the edge can be surprisingly weak. In theory, something could cross the event horizon of a supermassive black hole without feeling dramatic stretching at that exact moment. The danger comes much deeper inside. This leads to a key lesson. Bigger black holes are not more violent at the edge. In many ways, they are calmer. The physics is the same, but scale changes the experience completely. Another strange effect near black holes involves time itself. According to our best understanding of gravity, time slows down in strong gravitational fields. This is not science fiction. It is a real effect that has been measured near Earth using precise clocks. Near a black hole, this effect becomes extreme. From the perspective of someone far away, a clock near a black hole ticks more slowly. The closer the clock is to the event horizon, the slower it appears to run. At the event horizon itself, time appears to almost stop. Light signals sent outward take longer and longer to escape, eventually never reaching the outside observer. This creates the illusion that objects freeze at the edge of the black hole. From the perspective of the falling object, however, time feels normal. The clock ticks as usual. This difference in perspective is one of the most mind-bending aspects of black holes. Both views are correct, depending on where you're observing from. This is not an illusion. It is a fundamental feature of how space and time behave under extreme gravity. Once again, size matters. Near a stellar black hole, time dilation increases very rapidly as you approach the event horizon. Everything changes quickly. Near a supermassive black hole, time dilation builds up more gradually. The same rules apply, but the slope is gentler. This reinforces the idea that supermassive black holes are not instantly deadly environments at their edges. Physics near black holes also pushes our understanding to its limits. The closer you get, the more extreme conditions become. Gravity becomes so strong that it dominates all other forces. Space is curved so deeply that straight lines no longer behave as expected. Time and space mix in ways that defy everyday intuition. At the very center of a black hole lies the singularity, a region where, according to current theory, density becomes infinite and known laws of physics break down. It is important to be honest here. Scientists do not know what actually happens at the singularity. This is not because black holes are mystical, but because our current theories are incomplete. General relativity describes gravity extremely well, but it does not include quantum effects. Near the singularity, both gravity and quantum physics become important, and we do not yet have a complete theory that combines them. This uncertainty is part of what makes black holes so valuable to science. They act as natural laboratories for testing the limits of our theories. When physics breaks down, it points us toward new ideas and deeper understanding. Black holes are not failures of science, they are invitations to improve it. Another key difference between stellar and supermassive black holes is how long extreme effects take to become noticeable. Near a stellar black hole, the journey from the event horizon to the deepest regions happens very quickly. Near a supermassive black hole, it can take much longer. This difference in timescale again comes from size and curvature. Bigger black holes stretch space over larger distances. Throughout all of this, one thing remains constant. The laws of physics do not change. Gravity behaves the same way everywhere. The equations do not care whether the black hole is small or large. What changes is how those laws play out over distance and time. This consistency is deeply reassuring. It means the universe is not chaotic. It is structured, even in its most extreme places. Understanding what happens near black holes helps remove fear. These objects are not traps designed to destroy. They are extreme outcomes of gravity doing what it always does, pulling matter together, bending space, slowing time. When these effects reach their limits, reality becomes strange, but not arbitrary. Stellar black holes show us how violent extreme gravity can be when compressed into a small region. Supermassive black holes show us how the same gravity can create smooth, vast distortions of space and time. Both push physics to the edge, but in different ways. In the end, black holes remind us that the universe is not built for human comfort or intuition. It operates on principles that remain true, even when they feel unbelievable. Near black holes, physics does not break its rules. It reveals them more clearly than anywhere else, and that is the real fascination. Not fear, but understanding. Black holes are not the end of knowledge. They are the frontier. For a long time, black holes were thought to be eternal. Once formed, they were believed to exist forever, silent and unchanging, locked into the fabric of the universe until the end of time. This idea made sense. If nothing can escape a black hole, how could it ever lose mass? How could it ever fade away? But modern physics revealed something extraordinary. Black holes are not immortal. Given enough time, they can die. This idea begins with something called Hawking radiation, one of the most surprising discoveries in modern science. To understand it, we need to gently step into the strange world where gravity and quantum physics meet. No equations are needed, just patience and imagination. Empty space is not truly empty. Even in the darkest vacuum of the universe, space is alive with tiny fluctuations. According to quantum physics, pairs of particles constantly pop into existence and disappear again almost instantly. Normally, these particles cancel each other out and leave no trace. This happens everywhere, all the time. Near a black hole, something unusual can happen. If one of these particle pairs forms very close to the event horizon, gravity can pull them apart. One particle may fall into the black hole, while the other escapes into space. To an outside observer, it looks as if the black hole has emitted a particle. Over time, this slow leaking of particles causes the black hole to lose a tiny amount of mass. This process is what we call Hawking radiation. It is important to understand how gentle this process is. Hawking radiation is not an explosion. It is not a dramatic burst of energy. It is an incredibly slow whisper of loss. For a stellar black hole, the amount of radiation is unimaginably small. For a supermassive black hole, it is even smaller. But over extreme spans of time, this loss adds up. This leads to a remarkable conclusion. Black holes can evaporate. The smaller the black hole, the faster this evaporation happens. This is another counterintuitive result. A stellar black hole emits more Hawking radiation than a supermassive one. Why? Because smaller black holes have stronger curvature near their event horizons. The quantum effects are more intense. As a result, stellar black holes lose mass faster than their giant cousins. Even so, faster is a relative word here. A stellar black hole with the mass of our Sun would take far longer than the current age of the universe to evaporate completely. We are talking about timescales so large that writing them down almost feels meaningless. Trillions upon trillions of years. Supermassive black holes operate on an entirely different scale. Because they are so massive, their Hawking radiation is incredibly weak. Their evaporation time is vastly longer than the universe has existed so far. In fact, the lifetime of a supermassive black hole can exceed the current age of the universe by an unimaginable margin. Even when all stars have burned out and galaxies have grown dark, supermassive black holes will likely still remain. This is why scientists say that supermassive black holes will outlive the stars. They are among the longest-lasting objects in the universe. While stars shine and die, while galaxies merge and fade, supermassive black holes persist, slowly and quietly losing mass over time. This realization changes how we think about black holes. They are not permanent scars in space-time. They are temporary, cosmic objects, just like stars and galaxies. Their lifetimes are enormous compared to human history, but finite in the grand cosmic story. The idea of black hole evaporation also adds emotional depth to the universe's future. In the far future, long after star formation has ended, black holes may become the last remaining sources of energy. As they slowly evaporate, they release tiny amounts of radiation into an otherwise cold and dark universe. In this sense, black holes become the final embers of cosmic activity. There is something poetic about this. Objects born from collapse and darkness eventually fade away into light. Not bright light, not dramatic light, but a soft, final glow spread over unimaginable time. The difference between stellar and supermassive black hole lifetimes highlights their contrasting roles once again. Stellar black holes are short-lived by black hole standards. They will evaporate sooner, though still far beyond any current epoch. Supermassive black holes are the ancient elders of the universe. They will be the last to go, quietly shrinking long after everything else has vanished. This raises another fascinating idea. If black holes can evaporate, what happens at the very end? As a black hole loses mass, it gets smaller. As it gets smaller, its Hawking radiation increases. Near the very end, the process speeds up dramatically. The final moments of a black hole's life are still not fully understood. Some theories suggest a final burst of energy. Others suggest a quiet fade. Science does not yet have a complete answer, and that uncertainty is important. Hawking radiation sits at the intersection of gravity and quantum physics, two theories that do not yet fully agree. Studying black hole evaporation may be the key to unifying them. In this way, The death of black holes could teach us more about reality than their birth ever did. This idea also removes a common fear. Black holes are not eternal threats. They do not represent permanent destruction. They are part of a cycle: formation, growth, influence, and eventual disappearance. The universe does not trap matter forever. Even the darkest objects slowly return their mass to space. Seeing black holes as temporary changes our perspective. They are no longer monsters lurking forever. They are extreme chapters in a larger story. They show us how gravity behaves at its limits, and then they quietly step aside. In the far, far future of the universe, when galaxies have drifted apart and stars no longer shine, black holes may be the last complex objects left. And even then, they will not last forever. One by one, they will fade, leaving behind a universe that is simpler, colder, and quieter than anything we can imagine. So yes, black holes can die, not suddenly, not violently, but slowly, patiently, following the same rules that govern everything else. Their death is not an ending filled with fear. It is a reminder that nothing in the universe is truly permanent. Not even the darkest and most powerful objects ever created. And that idea expands curiosity in a profound way. If black holes can evaporate, if even they are temporary, then the universe is not static. It is a place of continual change, where even the most extreme structures eventually give way to time. At first glance, the differences between stellar black holes and supermassive black holes can feel distant from everyday life. They exist far away, operate on enormous scales, and seem disconnected from human concerns. But when we look more carefully, these differences matter deeply to us, not because black holes threaten our world, but because they help us understand how the universe works at its most fundamental level. They shape galaxies, test our best ideas about reality, and quietly influence the physics that underpins modern life. In many ways, black holes are not just cosmic curiosities, they are teachers. One of the most important reasons these differences matter is galaxy evolution. Galaxies are not random collections of stars. They have structure, shape, and life cycles. Some galaxies are full of young stars and glowing gas. Others are old, quiet, and red, having stopped forming stars long ago. For decades, scientists struggled to explain why galaxies evolve so differently. The answer, in large part, lies in the presence of supermassive black holes at their centers. Supermassive black holes are deeply connected to how galaxies grow and change. When a galaxy is young and rich in gas, its central black hole can feed actively. As it does, it releases enormous energy into its surroundings. This energy can heat gas, push it outward, or prevent it from cooling and forming new stars. Over time, this process regulates the galaxy's growth. It prevents galaxies from becoming too large, too dense, or too active. Without supermassive black holes, galaxies would look very different from what we observe today. Stellar black holes do not play this role. They are part of galaxies, but they do not control them. This contrast helps scientists separate local effects from global ones. By understanding which black holes influence star formation and which do not, researchers can build accurate models of how galaxies evolve over billions of years. This knowledge allows us to understand where our own galaxy fits in the cosmic story and why it looks the way it does. The differences between black holes also matter for understanding gravity and space-time. Black holes are not just heavy objects. They are places where gravity reaches its most extreme form. Near them, space bends sharply, and time slows dramatically. These effects are predicted by our theories of gravity, and black holes allow us to test those predictions in ways that are impossible anywhere else. Stellar black holes test gravity on small, intense scales. Supermassive black holes test gravity on vast, smooth scales. Both are essential. When observations near black holes match theoretical predictions, our confidence in those theories grows. When they do not, science advances. Black holes force our equations to confront reality at its limits. This is why black holes are so important to physics. They sit at the boundary between what we understand and what we do not. Our current theory of gravity works extremely well in most situations, but it breaks down at the center of black holes. This tells us that our understanding is incomplete. By studying black holes, scientists hope to discover new principles that unify gravity with quantum physics, two frameworks that currently do not fully agree. This pursuit may sound abstract, but it has real consequences. The technologies we rely on today, from GPS to medical imaging, exist because scientists once studied physics with no immediate application in mind. The equations that describe space-time were once purely theoretical. Today they are essential for satellite navigation. Studying black holes is part of this same tradition. It is an investment in understanding, even when practical uses are not immediately visible. Black holes also teach us about extremes, and studying extremes has always driven progress. Everyday physics happens in calm conditions. Black holes show us what happens when conditions are pushed to the edge. Matter behaves differently. Time behaves differently. Space behaves differently. By understanding these extremes, scientists gain insights that refine theories everywhere else. For example, understanding how matter behaves under extreme pressure helps us understand dense objects like neutron stars, and even the behavior of materials under high stress on Earth. Understanding time dilation near black holes reinforces our understanding of time itself, which affects technologies that rely on precise timing. The universe is interconnected. Lessons learned in extreme environments often echo back into familiar ones. There is also a deeper reason these differences matter. They remind us of scale and perspective. Stellar black holes show us how individual stars live and die. Supermassive black holes show us how entire galaxies evolve. Together, they connect the small and the large, the local and the cosmic. They remind us that the universe operates on many levels at once, and that understanding comes from seeing how those levels interact. This perspective has emotional value as well as scientific value. In a world where immediate results are often demanded, black holes stand as symbols of long-term thinking. Studying them requires patience, imagination, and humility. It requires accepting that some answers may take generations to uncover. This mindset is essential not just for science, but for society. Knowledge without immediate application still matters because it expands the boundaries of what is possible. It changes how we think. It shapes future questions. It prepares us for discoveries we cannot yet imagine. When scientists first studied electricity, they could not foresee modern computing. When they studied atomic structure, they could not foresee medical imaging. Studying black holes may one day lead to breakthroughs that feel just as distant today. Even if no direct application ever comes, the knowledge itself has value. Understanding the universe is part of understanding ourselves. It satisfies curiosity, builds culture, and inspires future generations to ask questions. Black holes capture the imagination precisely because they challenge our assumptions. They show us that reality is stranger and richer than it appears. The differences between stellar and supermassive black holes matter because they reveal how one set of physical laws can produce wildly different outcomes. They show us that complexity arises from simplicity applied at different scales. This lesson applies far beyond astronomy. It applies to systems, societies, and nature itself. In the end, studying black holes is not about distant objects alone. It is about understanding the rules that govern everything. From falling apples to orbiting galaxies, it is about testing ideas, refining knowledge, and embracing uncertainty. Stellar black holes and supermassive black holes are not just objects in space, they are mirrors, reflecting the limits of human understanding and the endless potential of human curiosity. By learning why they differ, we learn how the universe works. By learning how the universe works, we gain perspective on our place within it. And that, perhaps, is why these differences matter most of all. At the end of this journey, it helps to step back and see the story not as a list of facts, but as a quiet comparison between two characters in the universe. Two black holes, two lives, two scales so different that they almost feel like different worlds, and yet, at their core, they are built from the same simple rules. On one side of the universe, a massive star lives fast and bright. It burns through its fuel, layer by layer, fighting gravity for millions of years. When it finally loses that fight, the result is violent and sudden. A supernova lights up space, matter is thrown outward, heavy elements scatter into the galaxy, and at the center of that chaos, something small but powerful is left behind. A stellar black hole, born from death, compact, intense, a dark remnant of a single star's life. On the other side of the universe, something very different unfolds. There is no single moment of birth we can point to, no single explosion we can replay. Instead, there is a mystery stretching back to the earliest days of the cosmos. At the heart of a forming galaxy, matter gathers, gas flows inward, structures grow, and somehow, early on, an enormous black hole takes shape. It grows slowly, patiently, over billions of years. It becomes a supermassive black hole, ancient, vast, quiet for long stretches of time, yet capable of shaping entire galaxies when it awakens. These two black holes could not feel more different. One is small enough to hide inside a city, yet heavy enough to bend space violently. The other is large enough to swallow a solar system, yet gentle at its edge. One lives among stars as a scattered remnant. The other sits at the center of everything, anchoring the motion of billions of suns. And yet, when we strip away the scale, something remarkable appears. They are the same, not in size, not in age, not in influence, but in rules. Both are born from gravity doing what gravity always does, pulling matter inward, bending space, slowing time. Both have event horizons, points of no return shaped by mass alone. Both curve space-time according to the same equations. Both follow the same physics, written once and applied everywhere. The universe does not invent new laws for giant objects, and different laws for small ones. It uses the same blueprint and lets scale do the rest. A few suns compressed tightly become a stellar black hole. Billions of suns spread across a vast region become a supermassive one. Same rules, different outcomes. This is where quiet wonder begins. Because it means the universe is not chaotic. It is not arbitrary. It is consistent, even when it creates things that feel unimaginable. The same logic that governs falling apples and orbiting planets also governs the darkest, most extreme objects ever known. There is comfort in that, a deep, subtle order beneath the strangeness. One black hole tells the story of endings, the death of stars, the recycling of matter, the ongoing life cycle of galaxies, where stars are born, live, and die even today. Stellar black holes remind us that the universe is still active, still changing, still creating extremes in real time. The other black hole tells the story of beginnings, of a universe learning how to organize itself, of galaxies forming around invisible anchors, of ancient processes we are only beginning to understand. Supermassive black holes remind us that the universe has a long memory, stretching back to times we can barely imagine. Together, they frame the universe in time, from early cosmic mystery to present-day stellar death, from ancient giants to newborn remnants. They show us that black holes are not just objects in space, but chapters in a much larger story. And that story does not end with fear. Black holes are often used as symbols of destruction, but what we have seen is something more balanced. They destroy locally, but they also create structure. They regulate galaxies, they recycle matter, they test the limits of physics. They shine through the light of accretion, even while their cores remain dark. They are not villains, they are consequences. They also teach humility. There are questions we still cannot answer. We do not yet know exactly how supermassive black holes were born. We do not yet know what happens at the deepest center of a black hole. We do not yet know how gravity and quantum physics fully fit together. These gaps are not failures, they are invitations. Science is not finished. The universe has not given up all its secrets. And perhaps that is the most important lesson of all. Understanding black holes does not close the book on mystery, it opens it wider. Each answer leads to deeper questions. Each discovery reveals how much more there is to learn. The universe does not rush us toward conclusions. It asks us to stay curious. So when you think of black holes now, think beyond fear. Think beyond size. Think beyond darkness. Think of a universe that can build a city-sized object heavier than stars, and also build a solar system-sized object that quietly holds a galaxy together. Think of the same laws written once, playing out across scales so vast that human language struggles to keep up. In the end, stellar black holes and supermassive black holes are not opposites. They are reflections of the same idea, seen from different distances in space and time. One born from a star's final breath, one born from the universe's earliest ambition, both reminding us that reality is deeper, calmer, and more elegant than it first appears. And that is where this story should end, not with an answer, not with a conclusion, but with wonder.